In this lecture we will talk about the traction mechanics, that is, the required forces to accelerate and brake a train. And this tractive force, or sometimes referred to as tractive effort, is composed of two parts. One part is the running resistance, and the second part is the term required to accelerate or brake the train. MA stands for the equivalent dynamic mass, which is taking into account also rotating masses, that you have to accelerate rotating masses as well as the train itself, which means that the dynamic mass or equivalent mass is somewhat bigger than the static mass. Well, the running resistance is a formula describing the resistance of movement of the train. And historically, each railway company had their own formulas for running resistance. Today, people are more scientific, trying to make better models. This is just one model used in this course. It's not really the best model, but it's used in this course. And since we're talking about railway traction, we don't care if it's very precise or not. It's just a way of describing the resistances that we have. The first part is called the rolling resistance or the mechanical resistance. The second is the aerodynamic resistance. Then we have curve resistance and gradient resistance. The first part, the rolling resistance, has two parts. One constant part determined by the mass of the train and a constant, and the second part which is proportional to the speed, that is, it's increasing by increasing speed of the train. This is due to plastic deformation when rolling. You have friction in wheel bearings, losses in dampers and in rail substructure. So this is the rolling part of it. So when you roll a train and have electric traction motors still connected to the supply, you will get no load losses in the motor. So the no load loss in the motor, they are not taken into account when you calculate the rolling resistance or the mechanical resistance of the vehicle. So that is, no load losses in traction motors are not included in this kind of rolling resistance. The second part is the aerodynamic part, aerodynamic resistance. This is, of course, an important part, especially if you try to build high-speed trains and operate trains at higher speeds. It consists of the density of air, it has a cross-section of the train, and you have a constant depending on the design of the train. And then you have the speed in square, or the relative speed in square. This means, of course, that increasing speed means that the running resistance or the aerodynamic resistance of the train increases dramatically. And since we know that power is force times speed, we realize that power will be proportional to the cube of the relative speed. So operating a train at very high speeds means that this part increases dramatically. The aerodynamic resistance is also influenced by crosswinds, tunnels, and other trains it meets. Looking at this aerodynamic resistance for a typical train and compare it with a similar high-speed train, we can see quite a big difference. The most significant part of the resistance is for both trains the bogie wheel set interference. That is, it counts for most of the total part of the aerodynamic resistance. The second part is surface friction and also the underframe. For a normal train, you can see that the space between the cars is substantial or important, but that is of course removed for a high-speed train because you have no spaces between cars for those kinds of trains. What might be surprising is the fact that if you're looking at the rear and front of the train, so of course it's not a big part for this conventional train, and it's also even smaller part for the high-speed train. As a consequence, we could assume that it doesn't matter what the front and rear of a train looks like, and of course it's not that important, because if you realize the train is a long and slender design, like a needle from many points of view, of course it means that the shape of the front and the shape of the rear is not that important. But of course, for high speed in general, you try to build a very, very aerodynamically well-designed front, because the airflow you get might influence, for instance, the pantograph or other means or other issues for the train. So in general, you try to build a train with a typical high-speed front, but in fact, from the pure resistance point of view, it's not that important. The gradient resistance is for people that like analytical formulas, the best one, because then you can directly derive the formula for the gradient resistance. M, and then you have the gravitational acceleration, G, times sinus alpha. And since this angle is small, you can normally say that sinus alpha is equal to alpha, which means that you can have a very simple expression for the gradient resistance, depending on the slope of the gradient in per mil. Typical values of that S is 5, 10, 15, up to 17, 18 per mil perhaps. In some extreme cases even higher, but then of course you have trains in mountains and so on might be higher, but that's not normal. Normal would be 10 to 15 perhaps per mil as a maximum value. If you add all these running resistances, or add these resistances into the running resistance, you can calculate the power required for normal train operation. And this figure shows the running resistance for a typical train with 7 cars, 1 locomotive, 12 square meters cross-sectional area, and this constant for aerodynamic constant as 2. And we have the sum of all the parts here. The red part is the total running resistance with a 1% gradient, that is a 10 per mil gradient. Here's a gradient resistance, here's aerodynamic resistance, and as you can see, it increases by the square of the speed. The rolling resistance is pretty small, or relatively small, increases slightly by increasing speed. And you have the curve resistance, as for a 1,000-meter radius is pretty small, and of course for an even higher radius it's even smaller. In this case, we will calculate the total running resistance and power for 2 cases. The first one is 160 kilometers per hour, and we have no gradients. That means that we remove this gradient resistance from the total running resistance, and that means we have a running resistance of 45 kilonewtons, 160 kilometers per hour, and 3.6 to transform the kilometers per hour into meter per second. That results in a total required power of 2,000 kilowatts. That is 2 megawatts to operate a train at 160 kilometers per hour on a flat track. Assume now that we meet a 10 per mil gradient, just 10 per mil, 1% gradient. That means that we go to the red curve, and at 160 kilometers per hour we have 90 kilonewton running resistance. Put it into the equation again, we get 4,000 kilowatts, 4 megawatts. So as we can see from this simple calculation for steady state conditions, the power varies a lot along the line. Just a small gradient will influence the power a lot, go from 2 megawatts to 4 megawatts. And this variation of power is a typical electric traction load. If you compare with, for instance, electric power systems, in general, the loads are pretty constant, varies slowly by time. In a train operation and a railway power supply system, the loads goes up and down very rapidly, and you have sometimes you have zero power, sometimes you regenerate, sometimes you have 2 megawatt, 4 megawatt, and that is a typical feature for a traction load. That makes electric trains a little bit different as electrical loads on the power supply system than normal loads are. That was end of part 1, and we will now look into adhesion as a second part.